As part of our final assignment, we were asked to do a video talking a little bit about electronics and its potential future related to some topic of personal interest. I decided to look for something related to what I'm currently working on. This is artificial intelligence. More specifically, neural networks. Artificial intelligence, or AI, has been developed since the 1950s or the 1960s, and it has the main objective to give computers or machines intelligent behavior. In less abstract definition, most of the times AI scientists try to make machines to perform tasks such as recognition, let's say for example, speech recognition. You want a machine to know what you're saying and then do something with it. Face recognition. Other types of tasks could involve giving a machine a more human behavior, where it learns how to do things by itself and not by somebody else inserting that knowledge via some kind of way, let's say programming. Some examples of that could be how to walk, use tools, or even how to cook. AI has recently taken a bit spotlight when it comes to performing difficult day-to-day tasks with a machine or a computer, specifically neural networks, with its incredible capacity and flexibility when it comes to pattern recognition. This is because these problems don't have an exact solution and they are really hard and expensive to solve with a standard programming solution or with a normal regular computer. I'll do a brief explanation how neural networks work and then say why this has a lot of potential when you combine it with electronics. So what are neural networks? Neural networks are a series of algorithms or computational models that take some inspiration in the natural process of information processing that happens in our brains. They are a big part of artificial intelligence. So this is what a neuron looks like. The essential concepts we have to keep from this is the process of how neurons transfer information from one to another. A neuron receives information from the little branches that pop out of another neuron's elongated arm, which is formally called an axon. The point of this information transfer is to activate the body of the new neuron and make it send more information through its own elongated arm. The process in which information transfer happens is called synapse, and the process of the body reacting to this information is called activation. Now, after we've seen this biologic inspiration, we can take a quick look at the computational model. This is what the computational model looks like. It is beyond the scope to describe what each of these variables stand for, but we can generally describe that from left to right, the inputs, weight, and transfer function part simulates the synapse process, and the activation function, as it says, simulates the activation process that happens in a biologic neuron. This is how we process information with a neuron in a computer model. Now that we know what a basic neuron looks like in our computer model, we can multiply that model 1,000 or even 1,000,000 times, and that's how you get a neural network. You feed this network some kind of information, let's say for example an image, and you can teach this group of neurons to do something with it. You can teach it to recognize cats within a picture, dogs, cars, whatever. By now you may be wondering though, how does it do that? One neuron by itself doesn't have the power or the capacity to do this kind of task. But after we group a few thousand of these neurons, we can start seeing how the model starts doing these kind of incredible things. And even the more amazing thing is that this same model we have previously mentioned can be used to do a lot of other things. This is the real strength of a network. And this is what I wanted to get to because now I can compare it. Now imagine having a computer that has the electronic architecture designed to work as a neural network and not as a regular computer. If Do you want to make it more fantastic sounded? What if we could build a little electronic brain? AI researchers have been working on this kind of problem for a long time now. Why haven't we seen this kind of electronic brains? Well, the answer is easy. It's because it's really difficult to make. They are actually kind of hard and still not efficient enough to outperform neural networks running digitally in a regular supercomputer. As of late, though, researchers trying to mimic the human brain have been working on several different models that might make this change. Researchers at California claim that they have developed small electronic neural networks that can perform simple image classification. These electronic devices simulate 100 neurons. Bad thing is that if we expect an electronic device to have the same capability of a human brain, we need to have 10 to the 15 power of neurons. That's a lot. In Stanford, a model called NeuroGrid is a computer model that is able to simulate 1 million neurons. This is exciting because the power that it takes the NeuroGrid to simulate these neurons is way less than the ones from a regular computer. Regular computers take about 1 million watts to generate 1 million neurons. The brain, though, that has around 100 billion of neurons, takes only about 20 watts. Why would we want this kind of artificial intelligence circuit? One of the most incentive reasons is because when you develop a good AI electronic system, you're going to spend way less energy in the data processing, and this is going to make these circuits to be viable in medical purposes. Let's say quadriplegic people who have lost a way to communicate with their brains to their limbs and legs might be able to do it again with a low-power electronic neural network. The neural network would work as a bridge between the body and the brain of the person. Another possibility is that the direct control of prosthetic limbs might be possible for people who have suffered amputation or even people that were born without limbs. I'm Leonardo Clemente, and this video was about AI and its relationship to electronics. Thank you.